When an electric current flows through a conductor placed within a magnetic field, the wire experiences a magnetic force. This fundamental phenomenon forms the basis of many electronic devices, including motors and generators. The force results from the interaction between moving charges in the wire and the external magnetic field, and its magnitude and direction depend on the current, the length of the conductor, the magnetic field strength, and the angle between the wire and the magnetic field. Mathematically, this relationship is expressed by the vector cross product equation and in scalar form. For this experiment, the angle between the current and the magnetic field is fixed at 90 degrees, meaning that the force reaches its maximum value. The purpose of this lab is to experimentally determine the magnetic field strength of a given magnet by analyzing how the magnetic force on a current carrying wire changes with varying currents. By systematically adjusting the current through the wire and measuring the resulting force, a linear relationship between force and current can be established. From this relationship, the magnetic field can be calculated. Once the magnetic field strength is known, it will be used to predict the magnetic force under new conditions, such as a different current or wire length, to verify the accuracy of the experiment. Comparing the measured and predicted forces allows for an evaluation of experimental precision through percent error analysis. This investigation not only reinforces the mathematical relationship governing magnetic forces, but also demonstrates how theoretical predictors can be tested and refined through experimental methods.
For our materials, we used our capstone system. We also used the triple beam balance, a magnet assembly, the main unit, a lab stand, and current loops. To begin the experiment, the main unit was securely mounted on a lab stand using a rod with a diameter of about 1.1 centimeters or smaller, and then a current loop was selected, and its total length was measured before being inserted into the arms of the main unit with the foil strip extending downward. The magnet assembly was then placed on a digital balance with a sensitivity of at least 0.01 grams, and the setup was adjusted so that the horizontal portion of the conductive foil passed through the center of the magnet's pole region without touching the magnets. The power supply was then connected to the main unit, ensuring that all connections were secure and that the current was initially set to 0. With no current flowing, the initial mass of the magnet holder and magnet was recorded to establish a baseline measurement. The current was then set to -5 amps, and the corresponding mass was recorded. The current was decreased by 1 ampere intervals using until it reached 0 amps, with each new mass recorded in Table 1. After reaching 0, the current direction was reversed by switching the power supply cables, and the current was increased from +1 amp to 5 amp in 1 ampere steps, recording the mass at each level. Each mass value was converted to force using the force equals mass times 9.81 gravity, and entered into Table 2, and then the data were analyzed using capstone software by selecting manual entry, labeling the x-axis as current, which is A or amp, and the y-axis as force or N, and inputting all measurements to generate a force versus current graph. A linear fit was applied to the data to determine the slope, which was then used to calculate the magnetic field strength using B equals slope over L. To verify the accuracy of the experiment, a second trial was conducted using a different wire circuit and current to predict a theoretical magnetic force. The measured and theoretical forces were compared, and the percent error was calculated using percent error equals the measured minus the theoretical over the theoretical multiplied by 100. This comparison allowed for the evaluation of experimental precision and identification of possible sources of error.
Okay. For this experiment, we set our equipment, and then after that we changed the current to 5 amperes, which in our table would be -5, and as it went through, it would change to -4, -3, all the way to +5. So we collected our data in this table, and I'm gonna show it in just a second. So this is what it looks like. And then from these values, we were able to also determine what each part of this equation meant. So we basically broke down this equation to look like the y equals mx plus b equation, where this is what we broke down the values to, and then this is what we got. And then from there, we also were able to get this other table, which provided us with our percent error using our theoretical and experimental values. So using that information, for capstone, we selected manual entry and renamed the x-axis to current A and the y-axis to force, where we entered our experimental data from table 1, and then we were able to get a graph showing a linear trend between force and current. So we used the highlight tool to select all data points and get a linear curve, and the slope and intercept were obtained directly from the fitted line. So our M was equal to 20.6, and then we know that our L was 29.4 M. And then in order to get B, we did M over L, which was 20.6 over 29.4, which gave us 0.701 T. So the data followed a clear linear trend between magnetic force and current, confirming that Fm equals our formula. So basically that our formula was correct. And then the average percent error between theoretical and experimental forces was approximately 4.8%, which also indicates strong agreement between predicted and observed values. So small variations may be due to measurement inaccuracies or slight inconsistencies in the magnetic field along the wire. So for our discussion questions, the first one says, in what other ways can you know the percent error of your experiment? So we can calculate by using the average theoretical and experimental forces, the slope values, so compare experimental versus expected slope from theory, and the differences in measured magnetic field versus literature values. So if the next question says, if you experiment with different circuits, would this significantly change your magnetic field? Why or why not? The magnetic field should remain mostly the same if the magnet setup and distance from the wire are unchanged. However, differences in circuit geometry, wire orientation, or coil configuration could slightly alter the field strength because the magnetic field depends on current direction, distance, and the conductor shape. So to condense all this information, our group concluded that the experiment confirmed that the proportionality between force and current in a magnetic field. We also agreed that while small differences in setup could cause minor variations in B, the overall magnetic field strength is primarily determined by the magnet configuration rather than the electrical circuit itself. So percent error can be measured in several ways, but all supported the same conclusion that our experimental results closely matched the theoretical prediction.
The experiment successfully demonstrated the relationship between magnetic force and electric current in a current-carrying conductor placed within a magnetic field. The data collected showed a linear correlation between force and current, confirming the theoretical equation when the wire and the magnetic field were perpendicular, meaning at 90 degrees. From the slope of the force versus current graph, the magnetic field strength of the magnet was determined experimentally. The calculated value closely aligned with the predicted theoretical value, supporting the validity of the experimental design and procedure. Minor discrepancies between measured and predicted forces can be attributed to a systematic and random errors, such as variations in wire alignment, magnetic field uniformity, or balance sensitivity. Despite these limitations, the overall results verified that the magnetic force increases proportionally with current, as predicted by theory. This investigation not only confirmed the mathematical relationship governing magnetic forces, but also emphasized the importance of precision and control in experimental physics.